Okay, it says we are live. Let me do another sound check just to make sure. Yep, there it is. Okay, we are good to go there. Let me go ahead and unplug this since I won't be needing it anymore. And let's talk about what needs talking about. So there's actually a lot to go over since this is going to be the first of a rather long series. I don't know how long it's going to be, but we'll see. Okay, let's do a camera check. Can I see my hand moving around here? Yes, I can. Does it show up on the YouTube side of things? Yep, looks good. So that's sound and camera good to go. All right, so after a long summer break, Office Hours with Al is officially back, and for this school year I decided I want to start things off with physics. It is my most popular subject. It's usually the first subject any new student takes with me, and yeah, I just figured I might as well put all my physics content out there for the world starting this year. They did make some changes to the course, and I did read up on that, and I have a whole course plan. It should be linked in the description if I understood that correctly. The stuff I put in the description should still be there in the description of the actual live stream. So you can go preview that if you want, but I'm going to go over it later anyway. So I guess I want to go over just generally how I'm going to be doing things for this course and for office hours as a whole. So I'm still going to do the thing I was doing before the summer break with office hours, which is just take questions from chat if anybody has questions related to my areas of expertise: math, chemistry, physics, late high school to early college level. And that will be after the physics part of the stream. As for the physics part of the stream, it's going to be for AP Physics 1 and AP Physics C. The course plan I've linked is only for AP Physics 1, but that's because AP Physics C, at least the mechanics portion of it, is largely the same as AP Physics 1. So AP Physics 1 and AP Physics C and AP Physics C mechanics. I'm just going to call it AP Physics Mech for short. There's a lot of overlap between them. In fact, the biggest difference between Physics 1 and Physics C Mech is that Physics 1, as of this year, has added a new chapter, which is the chapter on fluids. That the Physics Mech students can feel free to skip. That last unit, according to my course plan, you can skip that. Other than that, the Physics Mech students will have to do calculus, whereas the Physics 1 course is algebra-based. I'm sure students already enrolled in these courses know that ahead of time, but just in case there's somebody out there who's watching this, I don't know, before the year that they plan to do AP courses, that might be useful information. For the course plan, there are also points where I mention things that the Physics 1 students can skip that are not going to be on their exam, but that's not necessarily true for the Physics Mechanics students. So I will point those differences out when we get to them, but they are not explicitly pointed out on the course plan, so sorry for that. Maybe I'll make a separate copy of the course plan and adjust it for mechanics if I have the free time. I spent most of yesterday just editing and making sure links were working and all that stuff for the course plan before I made it go live on my website. So, yeah, we'll see if I can spare the free time for that. I imagine it's mostly going to be a copy-paste plus additional stuff. Speaking of which, I will probably be editing some parts of the course plan as I go, so that's something to watch out for. A course plan. Subject to change. Subject to change. I'll try to mention during these live streams whenever there's an update that students ought to look at. What else did I want to say? Let me look at my notes. I probably should have organized my notes a little bit better. I just kind of wrote them in a random order. Some might be wondering, what about AP Physics C, Electricity and Magnetism, and what about AP Physics 2? Currently, there are no plans to do either of those, but if I were to do one of them, I would prioritize Electricity and Magnetism because Physics 2 is kind of an unpopular course and there just aren't as many students taking that course versus E&M. Then again, E&M might have fewer students just by virtue of the fact that fewer students are even qualified to take that course, and some of them graduate high school before they even have the chance to. But we'll see. That's a decision that can be made later. Now, up until yesterday, I was thinking of doing the Physics 1 stuff and then dismissing the Physics 1 students towards the end of the stream and going on for another half hour or so to cover like calculus-based stuff for the Physics C students. But I've decided against that because that's not the way I normally teach Physics C. Normally the way I teach Physics C is I teach algebra-based methods first, and then after the whole entire course is completed, I go back and teach the calculus when reviewing. I feel like that's a better approach because what I often see students do when you introduce calculus techniques to them is they will try to calculus their way through everything and either make problems more complicated than they need to be or just outright miss the point of the problem and get something completely wrong. So I think developing a good mastery of algebra-based methods first and really pushing your algebra to the limits to get a solid understanding of what it can do for you before you get out your calculus power tools is the better way to go about it. I was originally going to just teach the calculus along with the algebra against my better judgment because I was worried for students who have to do calculus-based problems in their classroom. But then I realized something last night, which is I'm not the first person to make AP Physics material on YouTube. Not even by a long shot. In fact, back when I finished my general chemistry course a few years ago, I even said that one of the reasons I wasn't planning to do the same thing again for physics was because there are so many other content creators for physics out there, and I felt like it would be reinventing the wheel. So, yeah, if you need calculus-based practice and you have a more immediate need, you've got plenty of other resources available, so I'm just going to actually stick to my guns and postpone the calculus. And that takes care of I've forgotten how I wanted to word that sentence. That takes care of discussing how I plan on covering the calculus for the Mech students. That will come later when we revisit every topic for review. Let me see. I'm looking through my notes here to figure out what I need to go over next. I can cross that out. I can cross that out. Oh, and another thing, now that I'm reading it in my notes, another reason to postpone calculus is, especially for physics mechanics, not so much for electromagnetism, but for mechanics, the AP test doesn't ask that many calculus-based questions. I've seen multiple choice sets where only 1 or 2 out of 35 questions on the multiple choice were calculus-based, and if I recall correctly, one of those 2 could be solved using algebra-based techniques, or could at least be solved using intuition, because, I mean, it's multiple choice. You don't actually have to show your work. If you have a good intuition about it, you could still pick out the right answer without knowing calculus. So, yeah, that's another reason not to emphasize calculus too heavily. On the free response, I've seen maybe 1 or 2 parts, not even a full question, 1 or 2 parts of a question that usually say something like, set up but do not solve an integral that could be used to calculate the final velocity of an object falling subject to air resistance. And that set up but do not solve part, the emphasis on do not solve, just goes to show that they're not trying to be a calculus course. That's what AP Calc is for. They're trying really hard to just get you to show them that you understand the physics of it. All the more reason to postpone the calculus-based techniques. Okay, now I can fully cross that out. That's for later. Questions in chat. So since I'm going to have a sort of lesson plan that I want to go through first, I'm probably not going to address questions from chat as they come in unless they're like directly relevant to whatever I'm talking about during the lesson. But if you have questions for unrelated topics, then I will go through that at the end once I'm done with all of the physics stuff that I plan on covering for the day. I will go back through that chat history and answer whatever math or chemistry questions I can. So if you don't mind waiting, that's when those will be addressed, after the planned physics lesson of the week. We can cross that off. What else? What else? That's for later. That's for later. That's for later. So many of these are just for when I go over the course plan. Okay, so what about the streaming schedule? So the streaming schedule, I'm going to try and make it just this time every Sunday. So be there or be square, or just watch the recording after the fact. That's all good too. If anything happens during a stream, like internet going out or power outage or whatever, and the stream just cuts off abruptly, I am recording these. I am making backup recordings of these lessons, so that will be posted whenever I regain access to my internet. So no worries there. If it happens really, really early into the lesson, then I will try to schedule a makeup stream sometime during the week if I have the time available. If not, we'll just have to wait until the next Sunday, which isn't too bad because, in my estimation, we should be finishing the whole course sometime early into the second semester, sometime around January, February, if not earlier, at least in my estimation. And if we do finish that early, my plan is probably going to be either cover a new course or just do a lot of reviewing. So that's for the case of power outages. Okay, I think we are ready to go to the course plan now. So let me open up that page. And let me switch scenes over here. Okay, so this used to be a Google Doc that I sent to my private students, but I didn't want to expose my Gmail address by posting a Google Drive link, so I decided this was better. So, AP Physics 1 course plan. The book problems that are going to be recommended here for you to try out are going to be taken from College Physics for AP Courses 2nd edition from OpenStax. If you click the link, you will get taken there. Oh, and I forgot to make this the kind of link that actually opens in a new tab. I will need to adjust that later if I can remember. So I strongly recommend that you go ahead and download the PDF. It's completely free. It'll ask you if you want to make a donation because, they do operate on donations. But if you don't want to, that's fine. You can just click go to your file and all that. So downloading the PDF will allow you to gain access to the book even when, for whatever reason, you don't have access to the internet. So I strongly recommend having that as a backup. Other than that, you can just go through the book's table of contents and just view it online and create an account. Just go to your book. And if you use the view online option and if you create an account, then you can do things like create your own highlights and notes and stuff. And I think it also lets you record your answers to the book problems and things of that nature. Let me see. I almost exclusively use the PDF version, so I don't know too much about how the online version works, but you can play around with it and figure it out for yourself if that's more your style. Okay, let me go back to, there we go. Going back to the course plan. So what else do we see here? I've got, first overview. I've got 10 units to cover, so I consider the first one to be Unit 0 because it's really not so much physics as it is general physics skills. Unit 1 is going to be motion in one dimension, or one-dimensional kinematics as it's sometimes called, projectile motion, also known as two-dimensional kinematics or motion in two dimensions, force, work energy and power, momentum and collisions, circular motion and gravitation, rotational kinematics and dynamics, simple harmonic motion, and fluid mechanics is the new one for Physics 1 this year. Physics C students, you don't have to do this. So you can skip Unit 9 once we get there. And you might notice that I go in a somewhat different order from the book and possibly a different order from your teacher if you're doing this in school. And I have my reasoning for that. Vectors are usually covered in the projectile motion chapter, but I like to cover vectors earlier so that when we go to projectile motion, it's not our first time seeing that stuff. And usually that helps the projectile motion chapter go by rather quickly because it just combines everything you learned from motion in one dimension for horizontal and vertical situations and uses the vector skills to combine that into a 2D situation. I think sometimes Circular motion is taught before work, energy, and power. I like to postpone that because I feel like it serves as a good review for force and energy. Putting it later allows it to kind of serve as a review. And simple harmonic motion can be taught earlier. You can teach simple harmonic motion as soon as you finish work, energy, and power, as a matter of fact, but I like to leave it for later because it also serves as a little bit of a review. And I wanted to open up rotational kinematics and dynamics because for the Physics C students, here is an example of something. Yeah, over here. Center of mass intuition, no need to calculate it for the exam. This is only true if you are in Physics 1. Physics 1 students do not need to calculate the position of center of mass. We will learn what that even means when we get to that chapter. Physics C students, you will need to learn how to do this using both algebra-based methods and calculus-based methods. So we will address that when the time comes. But the point is, Physics C students should be taking this stuff with a grain of salt. And while I have this open, I guess I might as well just kind of go over how I structured this. So first you've got the topics under each unit. Pretty simple bullet points. Reading, this is from the OpenStax textbook specifically that I just showed you earlier. So I have certain sections that I recommend reading. I know reading textbooks is not everybody's cup of tea, but I think learning how to read through a textbook is a very important skill to develop. I think that being able to, open your book, go to a chapter, let's say chapter 6, for example, and going over here to a section and just kind of looking at the little headings, recognizing, okay, this is a worked example. Maybe I don't want to read all this stuff, but I might want to look at a worked example just to get a feel for how to solve problems with the equations I've learned, and maybe even try some of these FET simulations that they link to. I link to some of these myself in the course plan. Take note of any equations you might see, and most importantly, if you really don't want to read at all, you don't want to look at examples, nothing else, then at the very, very least, I don't think this chapter has any. If I go to, I think the force chapter might have something under friction. Where's friction? Oh, it's in chapter 5. Let's see, friction. I think this one has a table. Yeah, data tables like this. You're going to need these for some of the homework problems. So at the very least, make sure you skim through the chapter and look for this stuff so that you're not completely confused when you think a problem is not giving you enough information. Chances are they expect you to have data from a data table that was included within the chapter. So that's something to look out for. And let me cross that off my note list. But yeah, the reading overall, I mean, it's not homework per se, but I would suggest you at least take a glance at it. If for no other reason, just to develop the skill of teaching yourself stuff through a textbook. You're gonna need that once you're in college. If you're in an AP course, then it's highly likely that you're aiming for college, and in college it's a whole different ballgame. You don't spend as much time in class, but you are expected to spend a lot of time studying and learning on your own. So better to develop that skill now. If I had a nickel for every time I got college students who came to me saying, oh, I used to get straight A's without even studying in high school, but ever since I got into college, I've been struggling. Almost always, the problem is they never learned how to properly read a textbook and commit to a study schedule and all that stuff. Anyway, apart from the reading suggestions, I've got a bunch of videos and resources that you guys can look at. Mostly videos, but occasionally they will link to simulations and whatnot. And you're going to see a lot of those other physics channels that I was talking about that have already pretty much done the thing that I'm about to do with these next several office hours streams. And yeah, I hope you enjoy Flipping Physics and Michelle Van Biezen and occasionally Dr. Schuster as well, because honestly, I think if you have those, you've got pretty much everything you need, and maybe do a little bit of Googling for what's missing. But if for some reason you don't like their teaching styles, or you feel like there's something incomplete about them, then maybe I can fill in those gaps, even though I'm not entirely sure how I'd be doing so. Practice. These are just, I guess you could consider this homework, especially if you're a self-studying student. I would definitely treat this as homework in that situation. If you are enrolled in a class and you already have a teacher assigning you homework and all that, then I guess you don't need to do this as much if you're already getting practice that way. What I would recommend either way is you go through these and you look at the problems and you go, okay, I've seen this type of problem before, I know how to do it. I've seen that type of problem, I know how to do it. And then you see something that's got a little bit of a twist and you go, wait a minute, I've never done something like this before. Maybe I should try this one. That's kind of the approach that I would recommend if you don't have time to do every single one of these. Because when I listed these, I'm pretty sure I didn't mean for students to do every single one. I just listed every single one that I found that would be relevant for what students are expected to know for the AP exams. So by no means are you obligated to do, 4 versions of the same type of problem with the numbers rearranged unless you really need the practice. So if you see a problem type that you've already done and you know how to do it and you know you don't need the extra practice, feel free to skip around. This is supposed to be kind of self-guided, and I might go over some of these homework problems from time to time. But yeah, that's basically how you want to go about using this. Starred problems. Let me go to a section that actually has starred problems. Yeah, over here. So sometimes you'll see that I put a star next to the number of a problem or exercise that I wanted you to do. That might mean that it's a hard problem, or a problem that requires some extra thinking, or a problem that's noteworthy in some sort of way, even if it's not particularly hard. It just means there's something about the problem that you should pay attention to. But then again, most of this list is from a few years ago, so I guess when I actually look at some of these problems, I might end up being confused about what past me was thinking when he decided to put stars on these problems. But yeah, that's what the stars mean. In case you see those, just pay close attention. Maybe postpone that problem until you've done the other ones, because they might take more time. And just a general approach, whether the problems are starred or not, always ask yourself this when you do problems, because I don't make long lists of homework problems for my students to do just for the sake of torture. I try really hard not to, at least with my private students, I try really hard not to give them problems that I already know they know how to do in their sleep. I like to try and pick problems that excuse me. I try to pick problems that I want them to learn something from. So the question you should always be asking yourself at the end of any physics problem you do is, what did I learn from this? Because that's the fundamental problem with physics for a lot of students. It's not as straightforward as just memorizing equations. You need to really do a lot of problems and just learn through those problems how to use those equations and what kinds of things you can and can't do with them. Really getting to know the power of your toolbox and knowing, its potential and its limitations. Your toolbox is comprised of your math skills and your concepts and equations and all that good stuff, and problems are your opportunity to figure out what you can do with all that. So always be asking yourself at the end of each problem, did I learn something new from this, and what did I learn that I maybe took for granted before? Did I learn, for example, that that the calculation of kinetic friction is meaningless if I don't calculate static friction first to establish that an object is even moving in the first place? And if all of that sounded like nonsense to you, don't worry about it. It'll make sense when we talk about friction. Things like that. I'm not sure I can give you a very clear example off the top of my head that would be accessible to a student who has just begun their physics journey. Okay, let me look through my notes, and actually let me get some light over here. It's starting to get dark outside. I guess it's kind of cloudy today, at least where I am. Okay, we've talked about starred problems. I talked about the course plan and topic order, problems worth doing versus skipping, reading the book, and I already talked about the fact that I might adjust the course plan as I go. Talked about the practice and homework philosophy and how to pick problems. I already talked about those differences for Physics C. And I already talked about the readings. The readings are mostly suggestions, strong suggestions. And of course, just because a reading section is not listed in the course plan doesn't mean you don't have to read it, or it doesn't mean that you're forbidden to read it. By all means, if you want to read more, then go ahead and read some of those sections that I don't explicitly tell you to read. Just do so with the knowledge that that's not on your AP test, and if you try using those ideas on the AP test, you're probably not going to get credit, even if you happen to be right somehow. Other than the OpenStax textbook, I might pull problems from this book, College Physics by Surway and Fawn. And for the Physics C students, I might also pull questions from this, the 5th edition of Physics by Resnick, Halliday, and Crane. This one has an issue with wording some of their problems. They tend to word problems in a confusing way, but that's also another skill that you're going to want to learn for not only school, but for life in general. People tend to be very bad at explaining what it is that they want. And learning that sort of psychology skill of getting into the author's mind and trying to picture what they intended for you to do despite the confusing wording of some of the problems they wrote. That's a skill that is worth developing. We will see cases of that from time to time when I do some of those book problems for Physics C. and 2 more concerns, and I'll probably have other questions later that I'll address next week. What about significant figures? What about significant figures? My physics teacher cares a lot about sig figs. Al, what about the sig figs? What about the sig figs? I don't care about the sig figs. If you were doing AP chemistry, yeah, they're going to take points off for not following your sig fig rules. But for AP physics, they really care on the exam that you just demonstrate you know what you're talking about. Just show them something that remotely proves, especially on the free response, show them something that even remotely proves you understand what you're talking about, and they'll give you the credit. But if you're just kind of throwing random numbers together and it's clear that you don't necessarily know what you're doing, then yeah, you're probably not going to get the points that way. They even tell you to round. There's a value that we are going to use a lot throughout the course, which is the acceleration due to gravity, g, which is equal to about 9.8 meters per second squared. We'll make sense of those units when we get to that chapter. And some people like to write this as 9.81 to be more precise. On the AP Physics exam, a lot of times you can get away with just rounding this to 10 to make calculations simpler. In fact, there are problems that just assume that without even telling you, especially on the multiple choice. If you're not getting any of the multiple choice answers, then try going back and using 10 for the value of g, and maybe doing that, you'll end up with an answer that looks like one of the answer choices. Using 10 for the value of g is very common on the physics exam. They will allow you to get away with it. So yeah, worry about your sig figs when you are actually working for NASA or working on some other major project where calculations have to be super precise or else lives will be on the line. But you're just a student right now, so it's no big deal. So that's for sig figs, and last but not least, before we get started, I make mistakes. Let's put that in all caps. I make mistakes. I'm only human. I will get things wrong from time to time. If I catch those mistakes, I will correct them either live if I happen to catch them before ending the stream, or in like a pinned comment after the stream, or in the next stream. At some point, if I catch a mistake, I will correct it. But if you see me doing something that you think might be a mistake, feel free to point it out, and hopefully I will be paying enough attention to the chat to notice you yelling at me and see what needs fixing, if anything. And now, without further ado, let's finally get started. Done with introductions, let's actually get started with our topics for the day. And I should actually just open my course plan and look at it so that I keep track of what I have and haven't covered, because my short-term memory is not that good. My long-term memory is just fine, though. It's just the short-term memory that has to suffer for it. Anyway, vectors and essential math. That is our Unit 0. Vectors and essential math. And in case you've seen some of my previous office hours, I guess the one last thing I didn't address is, yeah, now I'm using pens because I felt like the Sharpies were smudging too much and becoming unreadable. So now I have an assortment of colored pens that I will be using. And yeah, I guess I'm going to need to stock up on these. I had one box ready to go, but I'm probably going to want more. Okay, now for real, let's get started. So, in the world of physics, there are two kinds of quantities that we work with. We've got scalar quantities, which is what a lot of us are used to up to this point. And then we have quantities known as vector quantities. What's the difference between the two? Well, scalars have magnitude only. They have something called magnitude, which is basically just an amount and a value. Did I say and a value? A value. I can't even talk properly today. This is why I'm not your English tutor. I say that, and yet there will probably be some mini English lessons throughout this course, as you will see. Vectors, on the other hand, have, I should have made those plural, scalars and vectors. Vectors, on the other hand, have magnitude, but they also have direction. And this will become more clear once I actually list some examples. And they have a direction associated with them. Okay, some examples of each. Examples of scalars include things like mass. Mass has a magnitude. You can measure how much mass something has. If I have, let me grab this thing. This thing over here has a total mass of 250 grams. This thing has a mass of 250 grams. The magnitude is 250 in units of grams. It doesn't have a direction. 250 grams left doesn't make any sense. 250 grams south doesn't make any sense. So clearly, mass is a scalar. Electric charge, which you're not really going to deal with in Physics 1 or Physics C mechanics. Length. Volume. Once we get to the fluids chapter, pressure is a scalar. It has a magnitude but not a direction, which is kind of unintuitive, but we will talk about how pressure works. It's very easy to start thinking of pressure as having a direction, but we'll get to that when we get to it. And we also have, I'll do distance. I probably should have written that on a new line. And speed. Wait a minute. Don't distance and speed have a direction too? I mean, I can travel a certain distance to the east or to the west or north or south, and I can have a certain speed while facing a certain direction, right? Well, actually, you're thinking of something else. We have separate terms for the vector versions of these two things. So let's take a look at examples of vectors. Examples of vectors include force. When I apply a force on an object, when I push or pull on an object, I'm pushing or pulling in a specific direction. So force has to have some sort of direction associated with it. Acceleration. When I accelerate in a direction. It'll make more sense once we get to the next chapter and talk about acceleration in more depth. Did I say accelerate? Acceleration. Acceleration. Vectors and scalars are nouns, not verbs. There's something we will learn about called momentum, which has a direction associated with it. We have something that we will learn about in the rotational dynamics chapter called torque, which you may have heard of before. It's associated with things like cars, and the rotation of their wheels, for example, or you may have heard of the concept of a torque wrench, which is a type of wrench that is designed to be easily rotated in order to tighten or loosen bolts. And I will add the counterpart to distance is what we call displacement. While the counterpart to speed is something called velocity. And it's not as simple as displacement being distance with direction included and velocity being speed with direction included. It's not that simple. There are actually some very important differences that you might miss out on if you oversimplify it like that. So let's first talk about displacement versus distance. Let's first talk about displacement versus distance. And I think it's about time to try out one of my new colors. Displacement versus distance. First, let's go over definitions. The displacement of an object, I guess I will go for this blue. Here's hoping that it actually works. I mean, it should work, it's brand new. Displacement is simply the difference, or I guess we could call it the change, in an object's position. The change in an object's position when moving between 2 points. I feel like I was writing faster with the Sharpies, but it's okay. When moving between 2 points. Okay. Distance, on the other hand, is what I would define as the total length of the path taken by an object moving between 2 points. I think the other downside of using pens is that it exposes my bad handwriting. I mean, my handwriting might not be the prettiest, but I do try to make sure that it's at least legible, although sometimes my V's end up looking like R's and I don't really have a good remedy for that just yet. So that's something to watch out for. So yeah, we're defining displacement as the change in an object's position when moving between 2 points, and defining distance as the total length of the path taken by an object moving between 2 points. The fact that it's a length, and length is a scalar, should tell you a little bit more about why distance is considered a scalar. But let's illustrate with actual physical scenarios. So let's say I have somebody who moves 3 miles to the east and then moves 4 miles, turns around a corner, and moves 4 miles to the north. So 3 miles east and 4 miles north. How far did they travel in terms of distance? Well, the distance they traveled would be 7 miles. Distance traveled is 7 miles. And it doesn't make sense to call this exclusively north or exclusively east. It's a little bit of both. It's just the total length of the path they took. If they laid out a string as they were moving along, and then that string just kept on unwinding as they walked and walked and walked, and then they cut the string at the end over here, and you measure the length of that string, the length of that string would be 7 miles. And it would probably cost a lot of money to have that much string. But, you know, it's not the most realistic scenario, but it was the best I could come up with off the top of my head. So that's the distance. What about the displacement? Some of you have already learned this and are ahead of me. Some of you, even if you haven't learned this in class yet, might already have an idea. Displacement is the change in an object's position when moving between 2 points. And how does an object's position change? Well, if something changes, that means it used to be something, and now it's something else. So whenever you talk about the change in something, you need to consider its final state and its starting or initial state. Starting, or the more commonly used word in physics, is initial state. Whenever you're calculating the change in something, you're calculating the difference between the final measurement of that thing and the starting measurement of that thing. And the thing being measured here, I guess, is position, or rather the change in position. So our position changed from here to here. How much change is that? Well, in terms of magnitude, your position changed by a total of 5 miles. How do I know this is 5 miles? You guys know your Pythagorean theorem by now. Otherwise, how did you even get into AP Physics, whether it's 1 or C? 3 squared plus 4 squared equals the hypotenuse squared. 3 squared plus 4 squared, 9 plus 16 is 25, is equal to 5 squared, so the hypotenuse must be 5 miles. Okay, that's good, but it didn't just change by 5 miles. That's not enough information. If I knew the starting position and I told you I got a displacement of 5 miles, I'd still be missing something. If I wanted to figure out the final position, I'd still be missing the direction, because I could go 5 miles this way, or 5 miles this way. There's actually an entire circle of points, and I'm probably not going to be drawing a very good circle here, but yeah, that's a very lopsided circle. But you get the idea. There's an entire circle of points that could be the final position if the only thing I told you about the displacement is that I'm 5 miles away from where I used to be. That doesn't tell me enough. So I need to specify a direction. And the way to specify direction, at least in a two-dimensional situation, is to give an angle. So I need to give this angle, and let me actually switch colors for that. Let's do this sort of dark reddish-brown color. I don't even know if this shows up well on the screen. It's distinct enough, I think. So yeah, I want to figure out this angle, and fortunately, you guys should know your trigonometry. You guys should know your trigonometry, and you should have, oh no. Come on, work with me. It's a brand new pen, come on, there we go. Yeah, there we go, now the ink is flowing. So we should be able to just use our calculators after setting up our trigonometry. This angle is part of a right triangle, so we've got the opposite to the angle is the side of the triangle that isn't touching the angle, so that's the 4 miles. Opposite is 4 miles. The adjacent side is the one that's touching the angle but is not the hypotenuse, so adjacent is 3 miles, and the hypotenuse is 5. I actually don't need all 3 of them, I just need 2. But hypotenuse equals 5 miles. And to figure out the angle, I can use any of my trig functions. SOHCAHTOA, sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. Sine of, I guess I will call the angle, let's call it theta. This is the Greek letter theta, and it's what we typically use for unknown angles, and if we have multiple unknown angles, then we might also use the Greek letter phi, or the Greek letter alpha, or even beta are sometimes used. So those are all Greek letters that we tend to use for angles, but the one you'll see most often is theta. Anyway, sine of the angle theta is equal to the opposite over hypotenuse equals 4 over 5. We can do cosine of theta equals the adjacent over the hypotenuse, which is going to be 3 over 5. Or we can use tangent of theta is equal to the opposite over the adjacent, in this case 4 over 3. And to get the angle, when you know the sine or cosine or tangent of that angle, what you do is you take the anti-sine, cosine, or tangent, and the way to do that, if you haven't done it on your calculator before or you just forgot, is you type in the one you want to use. So let's say I want to use tangent. So I want to do, instead of pressing the tangent button, I would do second or shift, as it may be called on your calculator, and now you have this tan with the -1 symbol. That's the inverse tan or arctan, and then type 4 over 3, and that should give you back the angle whose tangent is 4/3, and I'm getting 53.13 degrees. To test it out, if I just press regular tangent and I copy paste this number into it, I should get 1.333, which is 4 divided by 3. So yeah, it works. Something to note while we're here is that this only works because my calculator was in degree mode. So a lot of you are probably taking either pre-calculus or calculus at the same time that you're taking physics. In physics, we mostly work with degrees. There will be one chapter where we work with radians a lot more. Well, I guess 2, kind of. But yeah, your math class is probably going to work in radians more than degrees. So if you're switching back and forth between your math and physics classes, then just develop a habit of pressing this mode button every single time you open your calculator. And a lot of the time you'll be looking at yourself and wondering, why did I even click this thing? But then you'll look at the screen and you'll realize, oh wait, I need to switch modes. So develop that habit, even if it might be redundant to do it, even if you kind of become a nervous wreck and start pressing it when you don't need to. Better to check your mode when you don't need to change it than to not check your mode when you do need to change it. So make sure you develop that habit. Make sure you are in degree mode. I actually just had to check right now to make sure that I didn't accidentally switch it for my example. Anyway, so yeah, you've got, I mean, if you have any two of these three sides, you can use Pythagorean theorem to calculate the third side. So no matter what, if you have the information for two out of these three things, you'll be able to use all three of these. You have enough information to use any of them, but it'll usually be quicker if you skip having to do Pythagorean theorem in cases where you don't need to figure out this length, but you know these two things and you just want the angle real quick. That's when tangent is usually the most useful one to use, and that's the one I would recommend, but all of these will work. In fact, let's go ahead and test them. So we've got sine inverse, or arcsine as some people call it, of 4 over 5. That should also be, 53.1 degrees. And then for cosine of, or no, not cosine, inverse cosine of 3 over 5. And that's also 53.1 degrees. So 53.1 degrees. But this still doesn't fully tell us the direction. 53.1 degrees relative to what? Because I could have started facing this direction and gone 53.1 degrees this way, for example. I could have my 53.1 degrees here. That's a lot of arrows. That's probably needlessly confusing. 53.1 degrees on its own doesn't mean much unless you establish where that angle starts. So what I would say is that the displacement is 5 miles at 53.1 degrees north of east. And let me actually circle this so that it's not bunched up with everything else. There we go. 53.1 degrees north of east. Not east of north, north of east. From the east, I go north of that direction by 53.1 degrees. If you watch the flipping physics videos, you'll see Mr. P tells you to think of it as meaning from. Replace the word of mentally with the word from. North from east. Starting from the east, go north. East of north would have been, you start north and then you go 53.1 degrees east of there, and that's definitely not the direction that we have in our example. But yeah, there you go. There's a very basic classic case of displacement versus distance. Now let's take a look at another case. Let's say we are driving a car. Let's say you're driving a car, so this is like you're looking at it from a helicopter above, and the car goes to one of those pesky roundabouts. And I know, the civil engineers will tell me roundabouts are great and they manage traffic really well and all that, but I had to drive through a town that has a lot of roundabouts, and I don't miss those days. Especially during like high traffic periods, it was the worst because I could just never find the opportunity to get on. I'm probably going way too far in drawing this, but let's say, and I'll put a sort of center island here. Let's say that this car drives through here And let's say we start measuring its displacement from this point, and it goes around, it drives around, it drives, it drives, it drives, it drives, and then it comes here and exits. So its actual full path is going to look more like that, but I just want to measure what is the distance traveled and what is the displacement. That's not a good color. Let's use this one. What is the distance traveled from here to here? And what is the displacement if I'm going to say that the radius of this roundabout from the center of the island to the middle of the road, I'm going to say this is, what's reasonable here? 4 meters? Is 4 meters reasonable? Is that realistic? Possibly. Okay, if we said that the radius of this roundabout was 4 meters, how far did the car travel? Well, in terms of distance, it traveled half a circle, and this circle has a radius of 4, so we would do circumference of a circle is 2 pi r, so circumference equals 2 pi r equals 2 pi times 4, or I'm just going to call it 8 pi. You could plug pi into your calculator and get 24 point something, but I'm not going to do that. Actually, it would be 25 point something. But I'm just going to leave it as 8 pi. No need to plug in the pi unless you know you really have to. Try to avoid doing this, especially when we get to the rotational kinematics and dynamics chapter. There will often be cases where the pi is going to cancel out anyway, so leaving it as a pi instead of turning your numbers into ugly decimals is usually a good idea. Wait until you know you have to before substituting the value of pi. Anyway, so 8 pi would be the full circumference, but we only traveled half of a circle, so half of 8 pi, the distance traveled by this car, would have to be 4 pi, and I guess this is in units of meters, and I forgot to say meters over here. Okay, what about the displacement? Here's the initial point, here's the final point. How far is the final point from the initial point? I'm sure some of you are already ahead of me. It's 4 meters this way, and then another 4 meters over here. So the displacement is a grand total of 8 meters, and assuming I'm just using standard cardinal directions here, that would be straight to the east. The displacement is 8 meters to the east. If I just went 8 meters straight to the east from this starting point, I would get to this ending point. Of course, that doesn't necessarily mean that it's actually achievable in the physical world. I don't think the car would have an easy time getting over this island, and if this island isn't even, like solid, if this was just, say, a fountain or some sort of pond in the middle, then yeah, your car's not going through that, so displacement isn't necessarily the shortest distance between 2 points either. I don't agree with that definition, because if it was the shortest distance, it would also have to be, actually travelable. But I guess now I'm splitting hairs. Hopefully with these two examples, the difference between distance and displacement has become a little bit more clear. That's the ultimate goal of this page. And now that we have that taken care of, let's go over velocity versus speed, which are closely related to these concepts of displacement and distance. Let's go for, let's do this dark blue. Oh, I need to tighten this one first. That was about to fall apart. I'm glad I noticed. Okay, let's talk about velocity versus speed next. Velocity versus speed. So the definitions of velocity and speed are very directly tied to the definitions of displacement and distance. Very directly tied to the two. Velocity is the rate at which displacement increases or decreases. The rate at which displacement changes, to put it all in one word. The rate at which displacement changes, whether that change is an increase or a decrease, or no change at all. While speed is the rate at which distance changes, the rate at which distance changes. And both of these actually have two versions that we like to talk about a lot. We have something called average velocity, and we have something called instantaneous velocity. And similarly, we have something called an average speed and an instantaneous speed. If you are doing Physics 1, you only need to be able to calculate average velocity, but also have at least an intuitive understanding of instantaneous velocity and speed. But for Physics C students, you will need to be able to calculate instantaneous velocities and speeds. And we'll go over the calculus of that later once we finish the whole course. Okay, average velocity, we actually have a very simple equation for it. So we say V average, and I'm going to put a little arrowhead over the variable to indicate that it's a vector, is equal to change in position over change in time. I'll go over this in more detail in a minute. Change in position. I will call this delta, let's call it delta R for now. And that's a vector. I probably should have drawn the squiggle a little bit higher or written this a little bit lower. Over change in time. We will, again, expand on this in a minute. And then we've got average speed and instantaneous speed. Average speed and instantaneous speed. Average speed being defined very similar to average velocity, except this one depends on total distance. I will call that d over total time. Okay. So average velocity and average speed. What on earth do we mean by average here? Well, let's say, for example, that an object traveled around and zigzagged and went around and maybe did a little loop-de-loop and did whatever it did, and then in the end it ended up over here after starting over here. The average is the velocity or speed at which the object could have traveled to accomplish the same change in position or distance in the same amount of time. So let's say, for example, this thing took 35 seconds to travel from this point to this point, and let's say that this point was just, or that these 2 points are just straight, 1 point straight east of the other. I guess I didn't draw that too well because I can already see that my angle is off. Okay. We'll pretend that this was straight to the east. I probably should have just brought my ruler out and used that. Yeah, let me do that. The tools of the trade. Okay, that should be a little bit better. Okay, I know this is slanted upward a little bit, but let's pretend that this is straight east. Let's pretend that this direction is east. And let's say, actually, maybe I should just go ahead while I have the ruler out. Measure how far this is in centimeters. Oh, would you look at that? Exactly 8 centimeters. Okay, so this was a total of 8 centimeters. And so, I ask myself, if it took me 35 seconds to travel 8 centimeters, then how fast could I have traveled to the east to accomplish the same thing, but only moving in a straight line? We would just take the total displacement, which is our 8 centimeters. Total displacement, 8 centimeters. Over, so this change in time, the reason it's called delta t over here, the reason you've got this triangle symbol in front of it, is because sometimes you're using a timer or a stopwatch and the motion actually starts before this point. Say maybe the object was moving like this before this point, and then maybe it continued moving afterwards after that point. And you just started the stopwatch here, or you started the stopwatch here, but then you did like a split over here, and then another split over here, and then the thing finally stopped moving and you stopped the stopwatch for the final time over here, for example. Then you would have 4 different times on record. This time would be like 0 seconds on the stopwatch, and then this would be, I don't know, like 5 seconds later, and then this would be like the 40th second, and then this would be something like, I don't know, 52, for example. So the idea is that you take the final time, that is the time of the final point of the 2 points for which you're measuring the displacement, which would be the 40 seconds, minus the time of the initial point, which you reached at 5 seconds on this hypothetical stopwatch, and you would do 40 minus 5 to get that 35-second period. So that's what that's all about. Usually this change in time is just going to be the total time, but if you have a problem where, they give you like a table of values and they tell you, here's the time, here's the position, let's say they're moving along the x-axis and just moving straight to the right, and you know, they'll have like at 0 seconds, the object is at position 0, and then at 5 seconds, it's at position 10, and then at 7 seconds, it's at position 13, and at let's say 11 seconds, it's at position 8 again, which would imply that it actually went backwards between these 2 points, and so on and so forth. If they gave you a data table like this, and they labeled these points A, B, C, D, and so on, and they asked you, what is the average velocity between points B and D? Then you would go, well, 11 minus 5, 6 seconds is the total time between B and D. So that's what this final minus initial time business is all about. Anyway, that detour aside, we had 8 centimeters over T final minus T initial is just going to be that 35 seconds. 8 over 35, according to my calculator, that is about 0.2285. I'll just round it to 0.229 equals 0.229. And then this is in centimeters over, time was in seconds, so centimeters per second to the east. So if this object had simply traveled at 0.229 centimeters per second to the east for those same 35 seconds, it would have accomplished the same displacement. That's kind of how averages are. Averages are about pretending you lived in a world where everything was the same. If everything were the same, how would you get to the same total? Kind of like with average scores. If the average score on a test was 80, it's as if every single person in that class scored 80%, but of course we know that that's not actually what happened. Some people scored more than 80, some people scored less, and maybe nobody scored exactly 80, but there were just as many scoring above as below that it averaged out to that. So yeah, that's average velocity for you. Average speed would just be, well, actually average speed would be lower. Lower? No, hold on. For the same 35-second period, no, average speed over here would actually be higher. Average speed would be higher. So to get average speed, I would actually need to know the length of this squiggly path, which I don't know, but one thing I do know is that it's longer than 8 centimeters because, come on, this straight line distance is clearly a lot shorter than the length of this squiggle. Part of what lengthens this is you're kind of retracing steps going back and forth. You go a little bit north, but then you come back down south, and you go north again, and you go south again. All those retraced steps, they might not count towards displacement, but they do count towards distance. They are lengthening the total path. So this object traveled a path notably longer than 8 centimeters. I'm just going to come up with a random number for it because I don't want to get out a piece of string and waste time lining it up to this curve and measuring its length with a ruler. Let's say that this was, I feel like it would be about twice as long. Let's say this was about 18 centimeters. Let's say the total distance, let's say D is equal to 18 centimeters, give or take. And so you would take your total distance of 18 centimeters divided by your total time, which is still 35 seconds. That's the one thing that average speed and average velocity do have in common. And 18 over 35, let's check that with my calculator. 18 over 35, and I'm getting about 0.514 is what I will round it to. And I guess I should mention, since I did say earlier I'm not going to worry about sig figs, Usually my rule of thumb is 2 or 3 decimal places for most things, except maybe things that are supposed to be small, like angles. With angles, I probably won't go further than 1 decimal place because 1/10 of a degree isn't going to make that big of a difference in most situations. So that's just my convention. You're free to do what works for you. But I think 1 decimal place for angles and 2 or 3 decimal places for other quantities is usually good enough that you're not completely wrecking your calculations by rounding them too hard. Speaking of rounding, I should probably mention, because I have had students who forget how to round. So here's the number I got before I rounded it to 0.514. You look at the next number, and if it's less than 5, you just drop it. But if it's 5 or more, you increase. So if this was 0.5145 something, I would round it to 0.515. I would increase the last digit that I want to include in my rounded answer if the digit that comes after it is a 5 to a 9. A lot of students get in the habit of just dropping everything that comes after the last digit, and when they're supposed to round up, they forget to round up. So now you know, and now you have no more excuses. If anybody's gonna be in the chat, I'm not even gonna notice because I'm not on the right tab. Okay. So that's average velocity and average speed. What about instantaneous velocity and instantaneous speed? Well, those are kind of where your averages come from. So if we go back to the example of people getting an average on a test, people in a classroom getting their average for a certain test. Some score below, some score above. The average is somewhere in between the highest and lowest of scores. And those individual scores, you know, if we had like an average test score of 80 for a classroom, the people who scored, the 3 people who scored 71 and the 1 person who scored a 72 and the 5 people who scored an 83 and so on and so forth, those are, I guess you could call them like instantaneous test scores in a way. So instantaneous velocity and instantaneous speed is just your velocity or speed at a very specific moment that ends up contributing to the total that you use to calculate the average. So let's say, for example, I'll use blue for this. Let's say, for example, over here, this object is moving in that direction for that moment in time. Sometime later, they start moving downward, and now they're moving in this direction. So that's the direction of their instantaneous velocity at that point. Let's say I pick this point, for example. Instantaneous velocity would be in that direction and would have some sort of magnitude. When they're up here, just for a split second, their instantaneous velocity is straight to the right. Over here, it's, well, I guess down and slightly to the left at that point, and so on and so forth. So instantaneous velocity is the rate at which your displacement changes, the how fast you are achieving your displacement, and in what direction that displacement is being achieved at this instant, at a specific instant in time, hence the name instantaneous. So if I know how fast the object is moving. If this is a car and you just read the speedometer inside the car to know how fast it's going in miles per hour, then yeah, that's the instantaneous velocity, and it increases by a little bit and decreases by a little bit as you step on the gas or step on the brakes. That would be the magnitude of the instantaneous velocity, and the direction is whichever direction the object happens to be facing at the moment that the instantaneous velocity is recorded. Instantaneous speed is even simpler. It's just the magnitude of the instantaneous velocity. So instantaneous speed is just the magnitude of instantaneous velocity of, I'll just abbreviate it, inst velocity. While instantaneous velocity is magnitude and direction of velocity. Actually, no. Magnitude and direction of, I should call it change in displacement I feel like this definition is still somewhat flawed, but I think you get the idea is the most important thing. Magnitude and direction of change in displacement at a specific instant, at a specific instant. How fast and in what direction are you going at a very specific moment in time? Okay, so that takes care of average velocity and average speed and instantaneous versions of both. Let me see what else I have over here. I guess that is the end of it for now. Yeah, we'll talk about constant velocity and constant speed once we get into the one-dimensional motion section. But for now, this is enough just for the sake of introduction. Let's move on to more stuff relating to vectors. So I want to talk about representation of vectors, and I guess, well, now that I'm using, yeah, I can use the backsides of these pages now that I'm just using plain old ink instead of marker ink. I guess that's one positive for using pens. Now I can use both sides of the page and save paper. Actually, hold on. Yeah, I can use the backside of this first. Okay, visual representation of vectors. How do we represent vectors visually? I mean, we've kind of been doing it already. Visual representation of vectors. Okay, how do we represent vectors visually? What is the best way to represent them visually? Well, there are two key pieces of information that we need about a vector, and those two pieces of information are the magnitude and the direction. And the ideal visual for representing something that has magnitude and direction is an arrow. The best way to represent vectors, that I know of at least, is an arrow. Well, I guess I don't want to get into the stuff that you have to do for multivariable calculus right now, but I guess you could represent vectors just as ordered sets of numbers, but that's stuff that you don't need to know for AP Physics, even if you're doing the calculus-based version of the course. So let's say I drew an arrow like this. Well, we know what direction it's pointing in. So that's one of the two things we need nailed down. What about magnitude? The magnitude can be covered by the length of the arrow. If I draw two arrows in the same direction, let's see, this one is about 2.5 centimeters long, it looks like, if I'm looking at that correctly. And let's say I draw another one parallel to it, but I only make it 1 centimeter long. And let's call this vector A, and I'm going to put an arrowhead on top of its symbol to indicate that it's a vector. And let's call this B and put an arrowhead on top of it as well. Okay, so vector A and vector B, I can see that they have the same direction. And if I use my ruler to measure, then I can see that B has a length of 1 centimeter and A has a length of 2.5 centimeters. So 1 versus 2.5 would be, so vector B, the magnitude of vector B, is equal to 40% the magnitude of vector A is equal to 40% of the magnitude of vector A. It's 0.4 times as long as vector A, and I don't have to use centimeters as the unit. I can use this to represent anything. If, let's say, A is a force vector of, let's say A is a force of 20 newtons, and we'll go over what newtons are when we get to the topic of force, but just know that it's the unit for force. If A is supposed to represent 20 newtons, then those 2.5 centimeters translate to 20 newtons, which means what? Every 1 centimeter would be 2/5 of 20. So in this case, 1 centimeter of length is representing 8 newtons of force, basically. Every 1 centimeter on the scale of my drawing translates to 8 newtons. So that means, oh, and since B is 1 centimeter, that means it would have to be 8 newtons. And yeah, there you go. So length is a sufficient way to represent magnitude. If two vectors are parallel to each other, that is, they're facing the same direction, and one of them is, say, half the length of the other, then it's half the magnitude of the other. If you know the magnitude of one of them, you know the magnitude of both. So that's how we represent vectors visually. Arrows are very convenient because they convey both pieces of information that we need about a vector immediately. But that's not the only benefit for representing vectors this way. Another benefit of representing vectors in this way is that we get to now do addition and subtraction with these vectors more intuitively. The way vectors add and subtract is not as simple as it is for scalars. With scalars, if you have something like, say, you've got mass A is 3 kilograms and mass B is, I don't know, 7 kilograms, then you just add them and you get mass A plus mass B equals 10 kilograms. Straightforward. That spacing is weird between the 1 and the 0. Anyway, you just add or subtract them straight up and you're done. With vectors, it's not that simple. We saw earlier For distance, which is a scalar, all we had to do was add two distances, 3 miles east plus 4 miles north. In terms of distance, just added up to 7 miles. But in terms of displacement, maybe you didn't realize it at the time, but we actually just added two displacements. 3 miles to the east is the displacement from this point to this corner. And then from this corner to this final point is another displacement of 4 miles north. So you add this 3 miles east displacement plus this 4 miles north displacement. 3 miles east plus 4 miles north equals 5 miles at 53.1 degrees north of east. But how do we do that then? Well, Pythagorean theorem clearly works if the vectors in question are at right angles to each other. What if they're not at right angles to each other? What if I have two random vectors, say here's vector A, and here's another vector B, and why not, let's also add in, here's another vector C. How do I get the vector A plus B plus C? Well, visually what we can do is use something called tail to tip or tip to tail addition. Tail to tip, or as some people like to call it, tip to tail addition. It doesn't really matter which of the two you call it as long as you understand the idea. Tail to tip vector addition. So what you do is you draw the vectors starting with one of them. Let's say we start with vector A, and I'll try to faithfully redraw it, although I might be a little off in terms of length and direction. So I redraw vector A, and then the tail of the next vector connects to the tip of the vector that came before it. So I'm going to connect the tail of vector B to the tip of vector A and draw it immediately after like this. And there's vector B. And now I connect the tail of vector C to the tip of vector B. So tail of vector C over there, and that should be it. And the final sum of these three vectors, the sum, will simply be the vector that connects the last exposed tail to the final exposed tip. So if I connect everything tail to tip, then there should only be one tail remaining that's not connected to anything yet, and one tip remaining that's not connected to anything yet. And if I draw a straight line between those, let me get my ruler so I don't mess this up. There we go. That's our vector. I will call it vector D. This whole purple thing is going to be our vector D, which is equal to A plus B plus C. Okay, this is great and all, but if we do it this way, then we're going to have to use a ruler and a protractor every time we want to measure the magnitude and figure out the direction. So is there a simpler way using a little bit more math and a little bit less geometry? Yes, there is. But before I get to that, let's talk a little bit about subtraction. We will get to the more analytical method, but let's talk a little bit more about the visual method first. So apart from addition, we can also do subtraction. If I wanted to do, let's call it vector E, is equal to, I'm just going to do two vectors this time. Let's do A minus C. And the A and C I'm referring to are the same A and C from before. Let's say I wanted to draw vector E equals vector A minus C. How would I go about doing that? Well, to subtract a vector, all you have to do is flip its direction. The negative of a vector is simply that vector flipped. So A minus C is actually just A plus the vector negative C. And the vector negative C would be just, I'll draw it over here. That's your vector negative C. Just like that. Okay, so I want to draw A, and then connected to its tip, starting from its tip, I'm going to draw negative C, so that's going to look... I think the angle is a little bit too high for A, but that's okay. And then C is going to look something like that, or negative C rather. It's going to look something like that. And I connect the remaining exposed tail to the remaining exposed tip, and I get something that looks kind of straight to the right, but maybe up at a little bit of an angle. That's my vector E equals A minus C. So I can add, I can subtract. What about multiplication? We will get to it. Let me actually check with the course plan. I mean, it doesn't really matter in what order I do this from this point on. Yeah, I'll save the multiplication for last. We'll come back to this stuff. Let's see if we can now reverse this process. So earlier we added two vectors, 3 miles east plus 4 miles north, to get 5 miles at 53.1 degrees north of east. Can I reverse this process? Is there a way to reverse this process? If I know I have a vector, that's at an angle of 53.1 degrees and has a magnitude of 5. Let's call this vector, let's call it G. I guess I skipped F, but that's okay. Let's call this vector G, and let's say it has a magnitude of 5. Can I reverse the addition process? Well, kind of yes and no. If by reversing the addition process you mean actually figuring out the original vectors that were added to make G, then you're out of luck, because let me draw a copy of G over here so that it's not in the way of what I actually do. If I draw another copy of G over here, I can draw all sorts of pairs of vectors that would add up to G. I can draw all sorts of pairs. I could draw a vector that looks like this, added to a vector that looks like this, and that would add up to G. I could, let me use another color, I could draw a vector that looks like this, connected to a vector that looks like this, and those two red vectors would add up to G. there's an infinite number of possibilities here. I could draw a vector that looks like this, connected to a vector that looks like this, and that could add up to G. And this is assuming that G was made by adding just 2 vectors. How do I know that G wasn't made by adding 3 or even more vectors? How do I know that G wasn't made by adding, say, this vector plus this vector plus this vector plus this vector? So if by reversing the process you mean trying to figure out what the original vectors were that it came from, then no, you're out of luck there. But fortunately, we don't need that. We just need a convenient pair of vectors to replace this vector that we have over here. And the 2 most convenient vectors we can come up with for a 2-dimensional situation is one vector in a horizontal direction along the x-axis and one vector in a vertical direction along the y-axis. All I need to do is find 2 vectors, one horizontal and one vertical. And I know I drew over the point 1, but I kind of had to. Draw one vector in the horizontal direction and one vector in the vertical direction, and let those 2 be our replacement for this 2-dimensional angled vector. This is the most convenient choice because it forms a right triangle, and we know how to work with right triangles. We know our trigonometry. So if this angle is 53.1 degrees, then this vector is the opposite side. This vector is the adjacent side to our 53.1 degree angle. And I know my SOHCAHTOA. I can do sine of 53.1 degrees equals the opposite, which I guess I'm going to call the vector gy, because it's the part of g that's in the y direction, over the hypotenuse, which is just g itself, or rather the magnitude of g. Yeah, opposite is actually just the magnitude of gy. I think I forgot to mention that earlier. If you see absolute value bars surrounding a vector, that just means magnitude of the thing between the absolute value bars. And some textbooks will even use double absolute value bars. Maybe draw something like this. So yeah, if you see that, that just means magnitude. That just means magnitude. Done, done. Okay, where was I? Opposite over magnitude of g. And cosine is defined similarly. Cosine of 53.1 is equal to adjacent over the magnitude of g. And if I do a little bit of algebra, if I multiply the magnitude of g over to the left-hand side, then I get magnitude of g sine of the angle, I guess I'll call it sine of theta to be general, is equal to the opposite side, and magnitude of g times cosine of the angle is equal to the adjacent part. And I should actually go ahead and give the names for these. So these 2 things are what we are going to call the components of g. We are going to call these the components Let me do that in another color. Let's do orange. Let's do, how do I want to do this? Actually, I'll point to this. I already messed this up, didn't I? Let's do it here. Yeah, this and this. This vertical vector and this horizontal vector, these are called the components. Components of the vector G. To be more specific, we would call this the horizontal component of G, or sometimes we call it the X component of G. And this is what we would call the vertical component or Y component of G. So yeah, the opposite component of G is just going to be magnitude of G times sine theta to get the magnitude of the opposite, and to get the magnitude of the adjacent, same thing. You do magnitude of the whole vector G times cosine of the angle. And notice I call them opposite and adjacent components. I don't call them X and Y components here. There's a reason for that. It's because opposite and adjacent are not always necessarily the Y and X respectively. A lot of students make the mistake of assuming that sine of the angle will always give you the Y component and that cosine will always give you the X. That's not true. It depends on where the angle is. If I had used this angle instead, sine of this angle would actually have this bottom side as the opposite, while the right hand side would be the adjacent. So that's something to be careful about. Sine of theta always gives you the opposite component. Don't think of it as the Y component. Think of it as the opposite component. Cosine theta always gives you the adjacent component. Usually your angle will be touching the horizontal side, so usually the opposite will be the Y and the adjacent will be the X, but not necessarily. So make sure not to develop that bad habit. Do not develop a bad habit there. That could definitely ruin you at the most inopportune of times. Anyway, if I do magnitude of G is 5, multiplied by sine of 53.1, I don't think you'll be surprised at what you're about to see. So if I do, I'll even do it in front of you so you know there's no trickery going on. 5 times sine of 53.1 degrees. It's going to be a little bit approximate because this 53.1 is rounded. 3.998, that's 4. That's 4, so that's for the opposite side, so it has a magnitude of 4 of whatever unit. And then the adjacent side, I guess I will call this magnitude of Gx. It's going to have a magnitude of 5 times cosine of 53.1, which unsurprisingly is about 3. So there you go. We got the 3 plus 4, the 3 east plus 4 north. That gave us our 5 at 53.1 degrees north of east. So now we know how to break a two-dimensional vector into a pair of one-dimensional components. This is in the x dimension, this is in the y dimension. What benefit do we gain from that? Well, it turns out that when you only have 2 dimensions to work with, it turns out that all vectors within one of those 2 dimensions can add or subtract with each other really easily. If I have vectors, let's call them, what do I call them? let's call this one vector, let's call this vector k, and let's call that vector L. They're supposed to be horizontal, but I guess I drew them kind of slanted. And let's say we have this vector M, and let's say I have vector N, looks like this, and vector O looks like that, and vector P looks like this. Okay, adding between vectors of this group and vectors of this group would require just the regular tail to tip stuff that would end up giving us a little bit of a geometry headache, but any additions or subtractions between k, l, and m amongst each other are actually going to be really easy, because if all of these are in horizontal directions, then all I have to do, even if I did connect them tail to tip, here's what would happen. Let's say I wanted to do k plus l. Let's say I wanted to do k plus l. So here's k. Okay, and then at its tip, I want to start the vector L. So L is just going to trace over it like that. And k plus L simply ends up being, here's where the exposed tail is, here's where the exposed tip is. K plus L just ends up looking like that, a short vector to the right. And because the only directions are right or left, all you have to do is simple addition or subtraction. In this case, you can think of it as vectors pointing to the right are in the positive horizontal direction, while vectors pointing to the left are in the negative horizontal direction. So you've got positive whatever to the right plus negative whatever to the left, and it looks like the positive is bigger, so you're left with a small positive to the right in the end. It's a really simple and direct addition or subtraction. If I wanted to draw something like L minus M next, if I wanted to do L minus M, okay, that's just L plus negative M, so I will draw L first. So that's L. And then negative M would be M just flipped over, so instead of right, negative M would be to the left, so that would just connect over here. And there you go. L minus M is just that. And you're done. If vectors are in the same dimension, all horizontal, then they just add or subtract the way intuition would suggest really easily. You don't even have to, all you have to do is figure out whether they're in the same directions or opposite directions and figure out if they're being added or subtracted, and then you can just work with their magnitudes directly, kind of like how you would do with scalars. Same story for if all the vectors are vertical, you can just add or subtract them to each other by simple addition or subtraction like you would with scalars. So separating everything into just horizontals or just verticals works nicely for us, because what we can do is we can deal with the horizontals separately and figure out their totals, and then we can deal with the verticals separately and figure out their totals, and then we will have one final horizontal and one final vertical. And if you have one horizontal and one vertical, what do you get? You just get a right triangle. And you can do Pythagorean theorem on that. So let's go ahead and look at what that might look like. Let's say I start with the following vectors, which I'm just going to make up as I go. How about vector A is at, let's call this a 40-degree angle. I might not have drawn it exactly at 40 degrees, but you know. And let's say this thing has a magnitude of, let's say this has a magnitude of 20 of whatever unit it may be. And let's say I have vector B, which looks like this, and let's say that has a magnitude of 23. Hold on, let me write it over here. Has a magnitude of 23 and is in a direction such that this angle is, let's call that 18 degrees. And let's say we have another vector C that just points straight to the right and has a magnitude of, let's call that, let's see, this versus this. It's about 2/3 of the way through it, so let's call this 14. Let's say C has a magnitude of 14. And let's say I want to find magnitude and direction of A plus B plus C. A plus B plus C. And let's call this vector R. Let's call this vector R, and you'll understand why I chose R later. Okay, so to do this without having to bring out the ruler and protractor, what we would need to do is separate A into its horizontal and vertical parts, separate B into its horizontal and vertical components, and separate C into its horizontal and vertical components, which is actually quite easy because it's already just a horizontal vector of 14 with no vertical component to it whatsoever. Okay, it does help to make a table when you're first doing this, but with enough practice you'll start to be able to do this without organizing it into a table. But for now, let's do X component, Y component, and I want 3 rows, one for A, one for B, and one for C. So we've got A, B, and C. Okay, C is the easy one, so C, its X component is 14, right? Or if you want, you can call this positive 14. And its Y component is 0, and when you have 0 of something, you don't have a direction whatsoever. So no need to specify a direction for a vector whose magnitude is 0. You could say it's in every direction and no direction all at once. You'll learn more about the 0 vector in your math class if you decide to do a lot of math in college. Let's see, and then we had, I guess we'll start with A. Okay, so A is going to have the opposite component over here is going to be the y component. I'll call it A sub y. The adjacent component is going to be A sub x. So I'm going to do 20 times sine of 40 gives me the opposite. 20 times sine of 40 degrees equals the magnitude of, in this case it would be AY. So 20 times sine of 40 degrees, and I'm getting about 12.856, or you know what, I'll round it to 2 decimals, 12.86. That's the y component, so that's 12.86, and its direction, well, we can tell because the original vector A was up and to the right, so its components must be up for one of them and right for the other. So this is 12.86 up, or positive 12.86 if that's how you want to think about it. And then I can do 20 times cosine of 40 degrees, and that gives me about 15.32. Next digit is a 0, so just drop 15.32, and this is to the right. Noting the directions is important. And then for B, we've got the opposite component is horizontal and points to the left. The adjacent component that's touching the 18-degree angle is vertical and pointing down. So I'm going to do, this is going to be BY, of course, and this we're going to call BX. And we'll do similar stuff to what we did over here. Actually, I should probably just write out. So we have sine of 18 equals opposite over hypotenuse equals magnitude of, let's see, the opposite in this case is bx, magnitude of bx over magnitude of the whole b is 23, and then multiply the 23 over to the left, and that's how we get 23 sine of 18. And then similar reasoning applies for magnitude of by being equal to 23 cosine of 18. You might have to write it like this as a fraction a couple times and then multiply the denominator over to the left before your brain starts immediately recognizing to just do hypotenuse times sine, hypotenuse times cosine. You might want to still think of it as you might still want to set it up as a division at first until you get used to that. But anyway, 23 sine of 18, 7.107, that's going to be 7.11 if I round it. And that is in the x direction, so 7.11. And then is it to the left or to the right? It's to the left, 7.11 left. Okay, and then let's do 23 cosine of 18. And I'm getting 21.874. We can drop since that's just a 4. So 21.87. And then the direction is down. Okay, 21.87 facing downward. And now we have everything we need to figure out whoops, not B. I meant to write R. There we go. Okay, so we need to figure out what the sum of these three vectors is by working one component at a time. So we've got 15.32 to the right, plus 7.11 to the left, plus 14 to the right. So adding 7.11 left just means subtracting from the right. So what I'm going to do is 15.32 minus 7.11 plus 14. So 15.32 minus 7.11 plus 14 gives me a total of 22.21. 22.21. And for the vertical, I've got 12.86 up and 21.87 down, so there's more down than up. So I'm going to do 21.87 minus 12.86, and I'm left with 9.01 down. And I probably should have specified the direction over here. This is 22.21 to the right overall. Okay, so now that I've added the horizontal parts separately and I've added the vertical parts separately, I'm left with one final horizontal and one final vertical. I'm left with one final horizontal and one final vertical. I've got 22.21 to the right. I guess if I'm remaining faithful to the original drawing, it should be a little bit longer than A, something like that. So I've got 22.21 like that, and then 9.01 down, so that's a little bit less than half the length of this, so that's going to be 9.01 down. And if I form a right triangle with this, then I can just use the Pythagorean theorem to figure out the final magnitude and with it the final direction, which I'm going to specify with this angle right here. I'll call it theta. Okay, final magnitude Pythagorean theorem gives us 22.21 squared plus 9.01 squared is equal to that number, and then if I take the square root, I'm getting 23.97. That does make sense. The hypotenuse does need to be longer than the two components that we got it from. 23.97, no issues so far. So that's the magnitude. And as for the direction, we can use any of our inverse trig functions. I would recommend sticking to tan inverse because, one, you can use it immediately before even having to calculate the 23.97, and two, if you made a mistake in calculating this 23.97, then if you reuse it using sine inverse or cosine inverse, then now you've got not only a mistake in the magnitude, but also a mistake in the direction. And it's just better risk management to not reuse your calculations more than you need to. Sometimes you don't have a choice. You have to calculate one thing in order to calculate another. But if you have the option to calculate things from just original information that was given to you, then that's usually the safer way to go about it, so that your mistakes don't end up multiplying, so that one mistake doesn't turn into two, that turns into three, that turns into four, that turns into a whole problem ruined. Anyway, I'm going to use inverse tangent, and let's see, opposite of this angle would be 9.01 over the adjacent to this angle would be 22.21, and I'm getting 22.08. I'm going to round that to 22.1 degrees, so I can't really write it in over there. There's not enough space, so I'll say theta equals 22.1 degrees. We can say this is, well, I didn't specify east, north, west, and south for this. We could do it in terms of cardinal directions if that's the problem we're working with. We could say this is 22.1 degrees south of east. If we're using cardinal directions, if we're just using coordinate systems, we could say 22.1 degrees below horizontal. And if you want to be even more specific, you could also say it's 22.1 degrees, instead of below horizontal, you could say it's 22.1 degrees below the positive x-axis. That's even more specific because it tells you that it's also to the right, whereas below horizontal only tells you that it's downward. It doesn't tell you if it's right or left. And sometimes that matters and sometimes it doesn't. So when it doesn't matter, you can just get away with below horizontal. You know, if we're talking about, like, say a cannonball that was fired off the edge of a cliff, below horizontal would make perfect sense for telling us like which direction it was moving at before it crashed into its target, because what other direction would it go? It's not going to go backward from the cannon. It's pretty obvious that it's to the right of the cannon if the cannon started, you know, on the left-hand side. If you have a cannon and it fires an object, and then you say the final direction that the cannon shot is moving is whatever degrees below horizontal, nobody is going to get confused by that and think that maybe it was this way instead of that way. So sometimes simply saying below horizontal is sufficient, or above horizontal, or whatever the case may be. But if you want to be specific and you're not using cardinal directions, then just refer to the positive versus negative x-axis or positive versus negative y-axis, and there you go. Where do I want to go from here? I don't think there's that much left. It's already been 2.5 hours. Wow, I guess I spent maybe a little too much time on introductory stuff. I mean, we are pretty much done with the topics. All that's left now is vector multiplication. And I guess also we need to talk about math skills, but I can save that for next time. Yeah, I think I'll save that for next time and just leave it as homework. So that's what I will do. Vector multiplication, and then maybe an example or two, and then we will wrap up here. And I actually don't have anything for my traditional office hours this week that I can think of, so I might just not do the follow-up part that I was originally planning. Maybe I'll start doing that as of next week. Okay, switch back to this. Maybe it's time for me to buy a third monitor, because 2 monitors doesn't seem like enough. And then once I get 3, it'll feel like a 4th monitor is needed. Okay, so vector multiplication. So we talked about addition and subtraction with vectors. What about multiplication? What about vector multiplication? There are 3 different types of multiplication that you can do with vectors. There are 3 types of multiplication that you can do with vectors. And multiplication also includes division because, well, I guess only the first type of multiplication includes division, because division can be thought of as just multiplying by 1 over something, multiplying by a fraction. Okay, vector multiplication. 3 types. The simplest type is multiplication of a vector by a scalar, or what we call scalar multiplication. And here is where we get the name scalar from. Scalar multiplication. If we do scalar times vector. And again, that scalar can be a fraction. So, scalar multiplication, a very classic example of it that we already saw, in fact, is average velocity. Average velocity is a vector that is equal to a scalar 1 over the change in time. That's a scalar. Time is a scalar. Well, I guess you could argue that time has a direction, but not in the sense that we define direction for vectors. If you're referring to phrases like moving forward or backward in time, that doesn't mean time has a direction. Time is considered a scalar as far as physicists are concerned. 1 over the time multiplied by the change in position, which you can call change in r, change in x, change in y. I like to just call it change in r, or sometimes change in s if I am dealing with a 2D or higher situation. If you're only working with an object that moves left and right, then I would call it change in x. If you're only moving up and down, then I would call it change in y. But if I don't know, or if I'm sure that it's not exclusively horizontal or exclusively vertical, then delta r is what I tend to use. But yeah, you've got a vector, which is change in position, multiplied by a scalar, which is 1 over change in time, and what you get from this is another vector. When you multiply a vector by a scalar, you get another vector. And there's usually no change in direction, but if there is a change in direction, then the only change possible is a reversal of direction. So another example that I could give is something that you won't learn in Physics 1 or Physics C Mechanics, which is electric force. Force electric is equal to electric charge, which is a scalar, multiplied by electric field, which is a vector. So you've got a vector equals a scalar times a vector. If the electric field is, let's say, to the right, and you multiply it by a negative charge, then the force that results from that is to the left. It'll be opposite to the direction of the field. If the charge is positive, it'll be the same direction as the field. Those are the only 2 things that can happen with scalar multiplication. The resulting vector is either the same direction as the vector that was multiplied by the scalar, or the exact opposite direction if that scalar happens to be negative. And we don't really have negative scalars in Physics 1 and Physics C mechanics. None that I can think of off the top of my head. Yeah, there's no such thing as negative mass. So, and no such thing as negative moment of inertia. That's for much later. Well, I guess you can have negative change in energy. You can have a decrease in energy, but I can't think of any situations where you would multiply change in energy by a vector to get another vector off the top of my head. So I'm going to say no, we don't actually see negative scalars multiplied by vectors in Physics 1 or C Mech at all. Now, as for why scalars are called scalars, it actually comes from this scalar multiplication. So if I have, for example, vector A over there, and if I multiply it by the scalar 3, if I do 3a, well, then the result is the vector 3a, which is just 3 times as long and has the same direction. I guess I tilted it up a little bit, but it should still be at that 40-degree angle. And the only thing that really happened was you kept it in the same direction, but you scaled up its magnitude by a factor of 3. And if this was a fraction, if this was like 0.1, then that would be scaling it down. Hence why these numbers by which you multiply vectors are called scalars. They scale the length, i.e. the magnitude of the vector. That is why they are called scalars. So scalar multiplication is the simplest type of multiplication, and we will see it quite a bit. We've already seen it with the definition of average velocity, and we'll see it again soon when working with acceleration, and then 2 chapters after that, we'll see it again in Newton's second law. Okay, so that's one type of vector multiplication. Then we've got our second type of vector multiplication, which is the scalar product. Not the same as scalar multiplication. Scalar product, also known as the dot product. Also known as the dot product. Do not confuse scalar product with scalar multiplication. Scalar multiplication is multiplying by a scalar. Scalar product is a vector times a vector. Is actually a vector times a vector, and it's called a scalar product because product is the name of the thing that you get from multiplying 2 or more things. A scalar isn't what gets multiplied in here. A scalar is what comes out of the multiplication. The product of the multiplication is a scalar. So dot product, the one classic example that we will see, and actually I think it might be the only example. Is it? I might be drawing a blank here, but the one example that I can guarantee we will see is the scalar known as work. Work is a dot product, and it is the product of force multiplied by displacement, and we use this dot symbol to represent the multiplication, and that's why it goes by the other name of dot product. So we've got 2 vectors, and we multiply them in such a way that their result is a scalar. So to take a dot product, there's one way you can do it if you studied vectors in your math class in pre-calculus, but if your pre-calculus teacher skipped that chapter, then you probably won't see that until college when you do multivariable calculus. So we're not going to deal with that. As far as physics is concerned, we only care about this version of the dot product formula. You take the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by the cosine of the angle between their directions. So if I had, force in this direction and displacement in that direction, then the angle I would use, the theta that I would use here, is the angle between the two, is this right here. A lot of students get confused on that because sometimes they'll have like the forces drawn on a box and they'll tell you the force is at some angle above the horizontal level. Let me draw that in, let's do orange. And they'll say, this is the angle between the force and the horizontal direction, and then they'll give you another angle between the force, or between the displacement and the horizontal direction, and people will plug one of those angles in when you're actually supposed to subtract those two to get that little angle in between the two vectors. And if that all went over your head, don't worry about it. We will see it again when we get to the work and energy chapter. But yeah, the other thing to talk about is this dot symbol. So if you're used to drawing these dots to show that you're doing multiplication, I would caution against that. I would recommend when you're trying to multiply things, at least what I'm going to do whenever I multiply things, is I'm just going to put them in parentheses. If I want to do 3 times 7, I'm going to write it like this. I'm not going to do 3.7, and I am not going to do 3 cross 7, because in physics, this dot and this cross mean something else. And speaking of the cross symbol for multiplication, let's talk about the third and final type of vector multiplication that you won't see until the second to last chapter if you're Physics C, third to last if you're Physics 1 in the rotational dynamics chapter. 3. The vector product. You can guess from the name that the product of this multiplication is going to be a vector. This is also called the cross product. I think you can guess why. And it also, just like the scalar product, results from a vector times a vector. Vector times vector. How do you multiply vectors? How on earth do you multiply vectors? The example we will see of this is torque. So torque is going to be the cross product of force and something called lever arm, which is the distance between the axis of rotation for an object and the point where the force is actually acting on it. So to give you an intuition for this, think about swinging doors open. You typically try to open it as far from the hinges of the door as possible, because that way you get it to rotate more. You generate more torque on it depending on where you push or pull from. If you push closer to the middle or even closer to the hinges, you notice that it requires a lot more force depending on where you push or pull at the door. So that's what this lever arm is for. The farther you are from the hinges, the greater the lever arm, the less force you need to generate enough torque to swing the door open or closed, as the case may be. So as for the direction of a cross product is always perpendicular to the two vectors that make it, and you don't actually need to worry about it all that much for Physics 1. All you need to do is figure out whether the object is going to swing clockwise or counterclockwise, and you're good to go. But the way you would go about it is through something called the right-hand rule. You don't need to remember this until you do electricity and magnetism. But basically, if I take my right hand, it's called the right-hand rule for a reason after all, then what I do is if I have vector A, actually let me use my pens. Let's say this orange pen represents vector A, and let's say this blue pen represents vector B. Let's say it's like this. And what I do is I have my fingers pointing towards vector A, and then I just keep twisting my hand until my palm is able to curl towards vector B, like this. If I close my hand, I can touch vector B. And once that's done, my thumb, if I straighten it out, should be pointing in the direction of the cross product of A and B. And if that all went over your head, again, don't worry about it until you start studying electromagnetism. You'll see clearer examples of it later. I guess I can draw an example over here, so let's see. If I want, let's say vector A is in this direction, and vector B is in that direction. If I connect them tail to tail, that's important. If I connect vectors A and B like this, tail to tail, then fingertips in the direction of A, and already I'm able to curl my fingers in such a way that they touch vector B, so I don't need to rotate anymore, and my thumb is pointing out of the page straight up. So the cross product of A and B would just be pointing out of the page. Always perpendicular to the plane that is occupied by the two vectors being multiplied. As far as we're concerned, though, we don't need to worry as much about the direction of the cross product. Instead, we are more concerned with the magnitude of the cross product. So the magnitude of a cross product is simply equal to the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. So for my vectors A and B over here, that angle would be this right here. Also, something to note about cross products is that if you reverse the order of multiplication, you do change the direction of the resulting vector. F cross R is not the same as R cross F, and actually come to think of it, I wrote this wrong. I just realized this should actually be R cross F. Yeah, it should actually be R cross F, not the other way around. If you reverse the direction of the multiplication, then you get the exact negative of the result that you should be getting, and the only consequence of that is that you calculate the wrong direction for your vector. It's just a simple plus versus minus. Is it pointing in one direction perpendicular to the plane? In the case of my A cross B example over here, we said it's pointing outward. If I did B cross A, that would be pointing into the page. So yeah, A cross B equals the negative of B cross A. So the order of the multiplication does actually matter for the vector product in determining the direction of the resulting vector. Speaking of resulting vectors, I think I forgot to tell you guys why I called this vector over here R. The sum of a group of vectors, and that also includes differences. If you add or subtract a bunch of vectors, then the final vector that you get from that is called the resultant vector, and that's why I called it R earlier. I forgot to mention that, sorry. Better late than never. So if you come across the term resultant vector, if you see a book problem that says, find the resultant of these vectors, that just means add them up. And I think that is where we will have to call it a day. I was hoping to also cover Math Essentials, but I'm kind of tired out. Otherwise, I would have just kept going and covered the Math Essentials and maybe even go over some of my stuff that I had ready for traditional office hours, but maybe I can do that next week. We will see. So, yeah, that's it for me. Go ahead and look at the... Actually, let me look at it myself. Go ahead and look through the Unit 0 practice materials. And actually, the Math Essentials for Physics is the last item under practice. Let me actually switch screens here. So if you open Unit 0, I think I've covered enough for you guys to be able to do all of this. The Math Essentials is really just a review of algebra, so let me actually talk about it real quick. So I just have, I guess you could call them sections instead of problems. Section 1 has a bunch of these problems where it's just making sure that you practice some algebra skills that are going to be really important for physics. Algebra skills that they might not teach you in your algebra class. Little tips and tricks and strategies and stuff. I do want you guys to try these out on your own first. Some of them, I'll admit, I kind of wrote poorly. Like this one doesn't actually have a single solution. This has a solution set. So this one might give you guys some trouble. I think it had, 4 different possible combinations of solutions. So that's something to watch out for. The other one was this one. You can actually find a specific value for, I think it might have been K, has an actual numerical value, even though I didn't really intend for that to happen. I don't quite remember, but one of these 3 unknowns, H, K, or L, can actually be solved for, and you can get a number for it. Even though my intention was for you to just get an expression for it instead of a solid number, so that was one that I could have written a little bit better. But most of these should be good to go. And yeah, some geometry review at the end there. I do have solution videos for, let me see, should be for sections 3, 4, 5, and 6. But I would like you to try them before I post those solutions. Those solution videos are hidden, so maybe I will post them in the description of the next stream. But yeah, that should be it for today. Anything else I need to mention before wrapping things up here? Let me see. I think the vector addition simulation is self-explanatory. If you want to play around with it, you should be able to figure it out tinkering on your own. And yeah, these are just some problems that I wrote. Do pardon that they might look a little bit silly. I originally made them for middle school students, but they're still relevant for high schoolers, so I figured why not use them. So yeah, those homework PDFs, pretty good stuff to practice with. And really make sure you practice your vector decomposition, because you're going to be doing this all the time in Physics 1 and Physics C mechanics. Make sure you master this stuff. Make sure you can get to the point where you can look at this thing, where you can look at a vector and its angle and immediately go, magnitude times cosine gives you this, magnitude times sine gives you that. Like, until that becomes sort of an instantaneous process in your head, you haven't practiced enough. And usually that doesn't take too long to develop. You just need to kind of sit on it for a few minutes, usually, and you're good to go. If you just really hyper-focus on just figuring out, do I use cosine here or do I use sine? If you can master that, if you really focus on it, you should be able to, after just a couple of problems, master it in like 10 minutes. No exaggeration there. That was exactly my experience. I used to be confused on this stuff until I sat down and drew a bunch of random vectors and gave them random angles and started kind of recognizing the pattern. Anything else to talk about? No, I think that is it. So yeah, next time we will look at the math essentials and probably start Unit 1, Motion in One Dimension. So if you have any questions or stuff, I guess you can post that in the comments. But I will probably end up answering most of it in the next stream anyway, just by following the agenda. But feel free to ask, and if you ask in time before the next stream, then I'll make note of it so that I make sure to cover that stuff if I have an answer for you. Okay, let me switch back to this. And actually, let me just set this up for next time, because I'm probably not touching this camera again until next time. And there we go. I'll let you go. See you guys next week.